In collaboration with Mitsubishi Electric Research Laboratories, Team 2208 presents our project on integrated Wi-Fi communication and sensing. So what is Wi-Fi sensing? Wi-Fi sensing basically utilizes Wi-Fi compatible devices within an environment to work together and measure or detect the presence of surrounding moving or still objects. Wi-Fi sensing is being experimented for the use of indoor localization like security systems, motion detection, and even gesture recognitions. As Wi-Fi sensing is quite new within the agenda of sensing technology, it aims to be very beneficial in the future as it expands to simplifying sensing technology and providing more affordable solutions. Within our own project, we will be developing a simulation platform which will utilize Wi-Fi signals for the purpose of object or human detection. The disturbances created between transmitters and receivers within the output data from moving or still objects will be used to recognize motion and biometric measurements. The main goal of this experiment is to utilize Wi-Fi compliant data packets to test and develop object detection methods, which will be through the heavy focus on radar functionality and utilizing signal availability.
For the WiGig Toolbox approach, we explored the four main tools that the toolbox offers and decided to mainly focus on the QD channel realization, which includes a MATLAB application and allows us to configure properties to run different scenarios. Here we have a simple example of what the channel realization provides, and it contains features such as MIMO support, libraries management, which allows us to define what materials are used inside the simulated room, and also allows us to configure antennas positions and orientations. Here we have a moving target example obtained with a QD interpreter tool provided by the toolbox. Here there's two targets and we want to analyze how these signals interact with them. Since we're working with MATLAB and this is obtained using Ubuntu and Python, our current goal is to implement a simulation similar to this one using MATLAB and the QD channel realization to create a scenario where we can sense target inside a room.
Moving on to the design phase, the first step of the design phase was to develop our channel models, and this was done using the NIST QD realization software. We started out with our empty room scenario where we initialized receiver and transmitter positions and placed those into our CAD generated environment. And from the QD output of the software, we generated the channel impulse and channel frequency responses, which you can see here. And overlaying these together, you can see how the impulse response is varied as the node position changes. And then we did the same sort of process with the object room scenario, where we placed various objects, in this case tables, at different locations in the room between a receiver and a transmitter, and then modeled the channel impulse and channel frequency response of that. And you will notice in this case that the channel impulse response in this scenario is a lot more convoluted than the empty room scenario. And also within each of these scenarios, we have the ability to manipulate the material sensitivity, which is going to change how reflective different types of materials are, and thus varying the impulse response of the material of the scenario based off the materials in the room.
The last part of our design is trying to implement machine learning and predict the location of transmitters in the indoor or outdoor environment, and the difference of each environment according to the channel state information. By achieving this, we first use the QD channel realization software, inputting with the environment file generated by the CAD, node position and node location, and target base and joint in order to have a human skeleton walking in the room. And we will have the output of number of rays, delay, path gain, phase offset of each ray, and angle of arrival and departure used for visualizer. Next, we use the channel frequency and impulse response we have by the MATLAB to combine with the Wi-Fi signal under the standard of IO2.11 ECE standard to get the estimated CSI under different signal bandwidths by doing the convolution. Last step is training and testing with the CSI on the different signal-to-noise ratio with machine learning to get confusion matrix with random forest algorithm. And these are the estimated channel response and the 16-point quadric amplitude modulation after the channel modeling. And this is the confusion matrix for empty room. As you can see, with the higher frequency, the more accurate the machine learning can predict the position of nodes in the empty room. By looking at the table of the data frame, we can see it clearly that on the diagonal of each matrix, they are making higher density of the correct predictions. So they can make very good prediction. Even the CSV output in CSV is very complex and chaotic just by looking at them. However, when we are moving to the table scenario, the accuracy of predicting the environment need to be improved by adding more training datasets or increasing the carrier frequency to get more channels the information. Of course, by looking at the data, at lower frequency, the density of each prediction for every class is evenly distributed. Thus, due to the reason of incapability of building or having the L2.11 AD standard receiver, the best we can have is under the 160 MHz.